Harmonic excitation refers to a sinusoidal external force of a certain frequency applied to a system. The response of a system to harmonic excitation is a very important topic because it is encountered very commonly and also covers the concept of resonance. Resonance occurs when the external excitation has the same frequency as the natural frequency of the system, and it will lead to large displacement and can cause a system to exceed its elastic range and can fail structurally. A very common example that many people are familiar with is that of a singer breaking a glass by singing. Harmonic excitation is also very commonly observed in systems that contain a rotating mass, for example, tires, engine, rotors, and so on. So today we will look at the equations for the response of a single degree of freedom system without jumping to harmonic excitation. And we're going to use a spring mass model. So as I said here, we are working again with a simple mass spring system. We have a negligible damping on a frictionless surface. And here, because we're looking at harmonic excitation, the driving force F of t will be of this form. So we can see we have the mass, the spring, and here the driving force. Here in this equation, F0 is the magnitude of the force, and omega here is the angular frequency of the applied force. And so this frequency is often referred to as input frequency, driving frequency, or forcing frequency. But anyway, it will have a unit of radian per second. So here, the sum of the forces in the y direction is 0. So we have no motion in that direction. And we're gonna sum forces on the mass in the x directions, and that will give us this equation here. And so here we have an excitation force F cos omega t. And so the solution will be of the form of x of p here, with capital X here being the amplitude of the response. Then we will do work of substitution and factorization to get the total solution. So that's the form of the solution as long as the driving and natural frequencies are not equal. Here we can see we have two constants of integration, A1 and A2. And these will be defined with the initial condition, x of 0 and v0. So the final form of the solution will be x of t here. Note that the response of the system depends on the driving frequency, and we can use Maple's tools to compare the response of a system depending on driving frequency, for example. And we're gonna have a look at an example like that. In this first example, we have the known parameters, which are the natural frequency of the system, two driving frequencies. So these are the one we're gonna compare. It's gonna compare the response of the system depending on the driving frequency. And we have the initial conditions, so displacement, velocity, as well as the magnitude of the force. We are using the equation that we defined just previously, so x of t, and we're gonna use the driving frequency 1 and 2 and compare that. So to compare that, we will plot the result and overlay the two plots here, as we can see in this graph. So here in this plot, we can determine the displacement or the response of the system for each driving frequency. We see here that the waveform of the response can be very different for different excitation frequency. And it also shows that the amplitude of the motion change with the excitation frequency. In the next example, we will compare the analytical result with the resultant simulation with MapleSim. So we compare Maple and MapleSim. Here, the example is simple. We have, again, a spring mass system, and we want to compute the total response of this system. I want to plot the result for 10 seconds. And we have the known parameters here. So K for the spring, 1,000 Newton per meter, the mass, the driving frequency, as well as natural frequency and initial condition here for displacement and velocity. So first, the analytical solution. So here we're using Maple. So we know the parameters. So we will just set these parameters here into Maple. Use the equation that we know to determine here the natural frequency, to determine f of 0, and then we are using again the equation here of the total response. And then we are able to plot this here, x, the total response, for over a range of 10 seconds, so from 0 to 10 seconds. And here we go. And we can read on the graph here the maximum displacement here of 0.6 meter. Now we can do the same thing with MapleSim. So we've seen MapleSim yesterday. It's a simulation software that will allow you to modelize different parts of physics and to actually combine all of that together. It's using Modelica component, and it's based on the equation. So you have like the real physical response of the system. So let's have a look at MapleSim. So as I said, that's simulation tool where you can combine different parts of the physics. So here you have, for example, the sinusoidal signal. Then you have the force, the mass, and you can see it's the same parameters as we have in our example. So here 10 kilos. We have the initial condition here as well, with S the displacement and V the velocity. Here at the spring, same thing. We have the stiffness here, 1,000 Newton per meter. And we added a probe to record the displacement of the mass. So we run a simulation. And when we run a simulation, you can see we have this plot, which is like the same as what we have into Maple. And we can read as well here the displacement of the mass of 0.6 meter. So here you can see that we have the same results between Maple and MapleSim. So you can use Maple to do your analytical analysis of your system, and then you can use MapleSim to actually work on the simulation part. It's using the equations behind, so you will have a very accurate result as well.